In our next example, we're going to solve a probability involving the word at least, and we'll use combinations to set this up. So it says Danny's wallet contains 4 $5 bills, 3 $10 bills, and 2 $20 bills. If he selects 3 bills at random, determine the probability he chooses at least one $20 bill. So the probability that he chooses at least one $20 bill it might be easier to compute this as opposed to counting all the ways to do this. We'll do 1 minus the probability that he does not choose any $20 bills in any of his 3 picks. Alright, so let's find the probability that out of 3 picks you get no $20 bills. Which means all of the bills are something other than $20, right? So in the denominator, so let's see how many things we have to choose from overall. So I've got 4 here, 3 here, 2 here, so that'll be 9 bills total. So out of those 9 bills, we want to choose 3 of them for our set. So that'll build our denominator, which will end up being there's 84 ways of choosing 3 bills out of 9 bills total, and order doesn't matter here. So in our numerator, we want to find out the way of choosing bills where none of the bills are $20 bills. So again, order doesn't matter in the order that the 3 bills are chosen, it just matters that you choose 3 of them. And we want to count out of a set of all of them that are not $20 bills. So that would be the 4 $5 bills and then the 3 $10 bills. So there are 7 bills total that we get to pick from, and we only want to choose 3 of them. There are 35 ways to do that. So now we can do 1 minus 35 over 84, which will end up being then 49 over 84, which simplifies to 7/12. Finally, in our last example, let's take a look at a poker hand of getting a full house. So let's find the probability of getting a full house of any suit in a poker hand. Right. The probability of a full house. Let's build the denominator first. Out of the 52 cards in the deck, we want to choose 5 of them for our hand. So 52 choose 5, that would give us 2,598,960 possible poker hands. Out of all those possibles, let's find out how many satisfy being a full house. So as a reminder, for the full house, the requirements that you have 3 cards of 1 rank, and then 2 of another rank. I think in our example previously we were talking about having maybe, for instance, 3 10s and 2 7s or something like that. Let's take a look at the 3 cards of the 1 rank. There are 4 cards overall, and you want to pick 3 of them. And that's going to be true over all of the different possibilities. So there are 13 ways that you could do that. Whether or not that rank is a jack or a 5 or a queen or whatever. So there are 13 ranks possible. Once the rank is chosen, out of the 4 possible cards, you want to pick 3 of them for your set. Moving on to the other type of card, there are then at this point in time 12 ranks possible, and out of the 4 cards in that rank, you want to pick 2 of them to finish off your full house. For this first part, out of the 3 cards of the 1 rank, there are 52 ways of doing that. To getting 2 cards of the other rank, this value right here would end up being 72. So to find out how many ways that you can actually have a full house, we would multiply these together and you would get 3,744 ways of getting a full house out of the 2,598,960 possible poker hands. Now we want to simplify this probability. So for this one, I can at least see that 2 goes into both of these. But as opposed to dividing out maybe possibly a whole bunch of 2's, because both of these numbers are quite large, maybe we'll just simplify this by using the prime factorization. So the prime factorization of 3,744 is going to be 2 to the 5th power 3 squared times 13. Now, where did that come from? So when finding the prime factorization for a number, so first off I could see that this number was even. So first off I'm going to do is I'm going to divide out from this number as many 2's as I can until at that point in time the remaining value no longer can be divisible by 2. So then I'm going to check that remaining value to be divisible by 3, and if 3 didn't go in, then I would check for 5, 7, 11, and etc. So I'm just going to be checking, breaking down this into a tree, which I just left this on my calculator, but to kind of give you an idea. So first, when I broke this out like this, I got 2 times 1872. This number was still even, so I divided that by 2. I got 936. This number was still even, so I divided that by 2, and I just kept going, keeping track of how many times I divided by 2 before the number was no longer even. Then I started trying to divide it by 3, and so on and so forth, just keeping track of those prime factors. So this will be the prime factorization for the numerator. The prime factorization for the denominator was 2 to the 4th power times 3 times 5 times 7 squared times 13 times 17. So now we'll start simplifying this. So in this one, this 2 to the 4th will wipe out 4 powers of that, and I'll be left with 2 to the 1st power. This 3 will wipe out one of these factors of 3, and I'll just be left with 3 to the 1st power upstairs. These 13's will simplify, and then that looks like it. So then after I'm done simplifying any common prime factors, I'll be left with 2 times 3 or 6 upstairs, and downstairs 5 times 7 squared times 17, which would be 4,165. So then the probability of getting a full house will be 6 out of 4,165, which maybe just to put this in a slightly different context, that'll be 0.00144. So moving that over, you're seeing that there is less than a 1% chance that this happens out of all the different hands of poker. So kind of rare to get a full house.